let's talk about distances in R3, distances in three-dimensional space. So we have a point P1 is at x1, y1, z1. P2 is at x2, y2, z2. First, let me just kind of point out here that if we were just thinking in 2D space in the plane, the distance from x1, y1 to x2, y2, we should know how to find that. What you do is that you do x2 minus x1 and square that. You do y2 minus y1 and square that and take the square root of the whole thing. And this is very closely associated to the Pythagorean theorem, where x2 minus x1 is some side length, y2 minus y1 is some side length of a right triangle, and this then would be the length of the hypotenuse. So when you have 3 dimensions, very little changes here. Now to find the distance between these 2 points in R3, all you do is tack on an extra plus z2 minus z1 squared term under the square root. And so this right here gives us our distance formula in R3, distance formula in space. So let's just do a very, very quick application of this to find the distance between these 2 points here. So this is just going to be the distance from P1 to P2. That's how that notation means there. Is going to be the square root of x2 minus x1, negative 3 minus 4 squared, plus y2 minus y1, 5 minus 2 squared, plus z2 minus z1, 0 minus 1 squared. But by the way, I'm writing this the way the book does it in terms of you do x2 minus x1 squared, y2 minus y1, z2 minus z1. If instead you want to do x1 minus x2 quantity squared, and so on and so forth, that also works as well, because x1 minus x2 squared is equal to x2 minus x1 squared. So 5 minus 2 squared is going to be 3 squared is 9, 2 minus 5 squared, negative 3 squared is also 9. Simplifying this real quick, I don't know whether this simplifies down to anything nice. I just kind of made this one up. Negative 7 squared is 49. 3 squared is 9 plus 1, negative 1 squared is 1. So square root of 59, that doesn't simplify, but that's okay. So finding a distance between 2 points in 3-dimensional space, pretty straightforward task to do here. I think it is worth noting, we won't prove everything in this class, but I do think it is worth noting that proving our distance formula here is not too difficult of a task. It basically just boils down to using the Pythagorean theorem a couple of times. So suppose that here is our point x1, y1, z1, and we have a second point off here, x2, y2, and z2. What I want to do is to form some kind of box here, some kind of 3D prism. I might draw in some stuff back there. And so the thing that we, let me draw the little dot, 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 dot. Those are the lines you can't see through the prism. Such a pretty box. Okay, so take a look right there. So this is a triangle floating around in 3-dimensional space. This triangle floating around 3-dimensional space from this front right bottom corner to this back right bottom corner, sorry, front left bottom corner, back right bottom corner, and top right back corner. And so this triangle right here, the side lengths, and to make our lives easier, let's assume that, you know, x2 is bigger than x1, y2 is bigger than y1, z2 is bigger than z1. So the picture, you know, is okay and stuff like that here. If it's not like that, it's not too hard to patch things up. So the side length here, on this side, so this is corresponding to the change in z. That's z2 minus z1. And the hypotenuse here, this is exactly the length that we're trying to find. That you know, from here along the hypotenuse of the orange triangle up here, that is the length that we're trying to find. Well, what about, and of course it's going to be a right triangle. It's going to be a right triangle. Well, what about this side length? So this side length here is actually right there. And I'm going to take out a different triangle now. I want to look at that triangle that takes up half of the floor of our box right here. So if I pop out that triangle, okay, so what's going on here? This would be like the difference in the x coordinates. So this would be like x2 minus x1. This would be the difference in the y coordinates. This would be like y2 minus y1. By the way, maybe to make myself feel better about stuff, I can just slap absolute values on the whole thing if those ever end up being negative to make sure I'm talking about distances. I can do that there as well. But anyways, as soon as we get this, well, we know the 2D distance formula that, you know, I scribbled that down on this sheet of paper a couple minutes ago. The length of this hypotenuse is, you know, by Pythagorean theorem, square root of x2 minus x1 squared plus y2 minus y1 squared. And then this hypotenuse right there becomes the leg of this triangle. x2 minus x1 squared plus y2 minus y1 squared. And now what we do to finish off this is that we apply the Pythagorean theorem to this orange triangle. So the length of the hypotenuse squared, P1, P2, is equal to the, let me do it Pythagorean theorem. I square the length of the hypotenuse is equal to this side squared, z2 minus z1 squared, plus the square of this expression. Square of this expression is just to get rid of the square roots. And then to finish off the distance formula, what do? We take the square root of both sides. And so that is how we obtain the distance formula. Okay, so hopefully, and this is kind of an instructive thing to do. I think it is nice how the 3D distance formula is just apply the Pythagorean theorem twice. Okay, so to wrap up this video then, let's have you, sorry this got so marked up from the previous video, had lots of, the previous slide, lots of drawings on it. So our first pre-class problem in the section, I guess, of the entire semester, just have you find the distance between these 2 points, 3, 2, 6, and -1, 4, 1.